Sounds good. Morning, everybody. How we all doing?
Here.
Sounds good. So I'm trying something new today. You might see on the top that it says that we are also live on YouTube. Right? I am trying to stream this at the same time, so that way, once we're done with class, it'll just already be on YouTube, right? At least that's the goal. See if it actually works. Hopefully you guys were able to get to lecture 1, right, on YouTube last time. Did it post okay? Did everybody able to see it? It's okay if you didn't go to watch it. It's fine. Not gonna hurt my feelings. Everybody super excited for the start of NFL season? No? Nobody? No takers? No?
Sorry, I'm a soccer guy.
I don't know how. The Giants got the first Monday night game of the season, so I'm sure we're going to lose. It's going to be great. We want to have a great time. You're rolling.
Dr. D?
What's up?
My computer is, it's not allowing me to change the setting to start video. I'm present during class, but it keeps telling me that it's failing to start video. Please select on our video and camera settings. I keep doing that and nothing's changing.
Okay. That's
Sorry
fine.
about that.
No worries. Thanks for letting me know.
I'll try getting it fixed for next class.
Sounds good. More minutes and we'll get started. All right, 9:45. Pretty sure we are short a lot of people, but we're just gonna get going. All right, Lord, thank you for bringing us together this morning. Thank you for helping us get through this first week of classes. Pray that you would continue to bless the rest of our semester. Give us the concentration, the focus, and the determination that we need. Help us to run the race all the way through. In your name we pray. Amen. Okay. So we are here. We're day 2, right? It's all very exciting. Couple of things before I jump. Well, I'll share my screen while I'm talking. A couple of things while you guys are here, right? Okay. Hoping that you guys can see my screen. I'm pretty sure that you can. So there's a couple things different than last class, right? First off, you might notice that at the top it says live, not just recording, okay? I am streaming this to YouTube as we are going because it will be faster, because once class is done, it will just automatically upload the video for us, right? And so there won't be a delay there. It is a private stream, so nobody else can get in, so you don't have to worry about that. Right, so you don't have to worry about that. Okay, other than that, right, I said that we would talk about exams, right? So today we've got episode 2, Transformers. No, not that kind. Not that kind. All right, so we're going to recap last class, and we're going to talk about modeling mechanical systems, then get into transformers and translational mechanical systems and rotational mechanical systems. And because Thursday is Friday for this class, some fun stuff at the end, assuming that there's time, right? So here's our word cloud that we came up with last time, right? You guys do not have to put names on this stuff. That's fine. The labs are confusing. We'll go over labs a little bit. What is a system? System is a grouping of various elements that work together to accomplish some task. A dynamic system is one in which the output of the system depends on the inputs and the initial conditions. What else depends on inputs and initial conditions? Differential equations, right? Turns out that most of the physical world can be discussed mathematically as ordinary differential equations, right? At least for this class. We're not going to go into anything beyond ODEs, and we're going to really focus on linear ODEs because I'm lazy and I don't want to do the other stuff. That's it. You might have noticed, I don't know if you have, but I posted the first half of a dynamics review on the YouTube channel. So if you guys want to check that out, you can. Is there anything else? I think we're going to cover some stuff and hopefully clear some of these things up. But is there anything else that is a burning question that you guys have right now? Anybody? Okay. So these things are still due. I know that says the 13th. That's not correct. That should be the 16th, right? That's due next Wednesday. The correct date is in LoudCloud, so follow what LoudCloud says, right? When in doubt, do what LoudCloud says. Okay. So we've got a homework due a week from Sunday and a lab due a week from yesterday, right? So by tomorrow, please let me know if you haven't found a lab partner, right? Because you need to do this as a team of 2. Okay, so let me know if you haven't found one. Stay within your own section, right? If you're TOS, try to stay TOS. I understand that you might not know who else is TOS. Just ask around, talk to each other. You guys pick, right? Remember, the caveat here is that if you do poorly on the first one, I reserve the right to swap you out into another group, right, for the next lab, just so we don't dig ourselves into big holes. Right? So talking about the lab, right, the lab is the pendulum lab, right? So in LoudCloud, you have what you need to do the lab, right? What do I mean by that? Well, there's a handout there, right? And you should read the assignment, see what is asked of you. There's a video on YouTube, right? Dr. D and Professor Price do labs, episode 1, Pendulum Lab. You should watch that because that is a video of us doing the lab, right? Follow the instructions and complete the lab with your partner. Essentially, what you're going to be doing is you're going to be making a mathematical model for a pendulum angular position as a function of time. Okay, so you have a really exciting video where we have a pendulum and we swung it and you get to see the angle that it swings through, and you have to, you decide on your sampling rate, right? How often you want to take points, right? And just build the model in Excel. That's how I would do it. The other part of that is you have to do the mathematical model. And we're going to go over more of that, how to do that today, right? So you're going to want to build the mathematical model, and then you're going to compare the two. Compare your mathematical model to your experimental model using percent error and plugging in values, right, that you get from your experiment. Danny, if you want to use MATLAB, have at it. I'm fine with that. Okay. All right, so that being said, we are going to watch this because this concept of numerical differentiation is probably going to help you do the lab, right? It's going to be helpful. So let's watch this video.
Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
In this video, we're going to be looking through the basics of numerical differentiation. Now, what numerical differentiation does for us is it gives us an approximate derivative in a situation where it might be difficult or impossible to calculate an analytical derivative. What if we only have data points for our function instead of an actual function to use? Well, in that situation, there's no way to calculate an analytical derivative. And so we have to go another path. The basis of this, as for so many things in numerical methods, is the Taylor series. Now, what Taylor series says is that the function at some point, and I've just named that point x, is going to be equal to the function at another point. I'm going to name that x bar. And that's going to be related to the derivative of a function, again evaluated at that second point x bar, multiplied by delta x. And that delta x is just the difference in space between the 2 points. So this is delta x is equal to x minus x bar. And then we have some additional constraints based on higher order derivatives. And we can go on further, but I'm just going to end this with an order of delta x to the fourth. So if you wanted to go higher, just remember that the number in the denominator here is equal to the order of delta x factorial. So this is 2 factorial, this is 3 factorial, the next one would be 4 factorial, which is 24, and so on and so forth. Now, we'd like to use this in order to calculate a derivative, and we want that at a specific point in our data. So let's say that we're interested in the derivative at this point right here. I'm going to call this point I. So at point I, we're going to have an x of I, and that x sub I is going to yield an f sub I, which is just equal to the function evaluation of x sub I. And we can do this for other points as well. So let's say that we go 1 point to the right and start talking about I plus 1. This point right here is going to be I plus 1. And we're just going to name those values x sub I plus 1, which yields f sub I plus 1, which again is just the evaluation of this unknown function at x sub I plus 1. So with this nomenclature, let's go ahead and rewrite our Taylor series. We're going to evaluate our function at x sub I plus 1. So we say that f sub I plus 1 is going to be equal to f sub I. So all of our x bars are now going to be x sub i's. So this becomes f prime, but we say fi prime, and this just means f prime of x sub I, multiplied by delta x. And I'll go ahead and write out the rest for you. This delta x that we have here is going to be x sub I plus 1 minus x sub I. So we're taking this value x sub I plus 1, subtracting off this, and we get this little delta x. Now remember that what we're looking for here is the derivative. So we want to solve this equation for fi prime. So what I want to do is go ahead and isolate this term on the left-hand side of the equation. So I will end up with a negative fi prime multiplied by this delta x, which is going to be equal to f of I minus fi plus 1, and then we have all this other stuff. So finally, we go ahead and solve for fi prime, and we end up with these first two terms divided by delta x. So this is fi plus 1, which the sign has been switched because we're dividing through by negative delta x, minus f of I divided by delta x. And our next term here is this minus fi double prime multiplied by only one delta x divided by 2. And then we can keep out writing the rest, but really that's all that matters. So the important thing to note here is that we don't know what fi double prime is. So all of this, we're just going to throw away and call it error. And so we end up with an error that has an order of delta x. So we have additional error terms on here as well, based on the other derivatives, but they're all of higher order, meaning that they're at least delta x squared. So if we're able to decrease delta x, for instance, then those should disappear faster than this error. This first little bit here is what we call a forward difference. And essentially what we're doing with that is we're just connecting a line between these 2 points and calculating the derivative based on the slope of that line. Now, this is not the only way to tackle this problem. All
right, so I'm going to pause it there because I think that that's enough for you guys to use in going forward with the lab. You can also do a backward difference, which is similar to a forward difference. It just goes in the reverse direction. When you do numerical differentiation, right, you end up truncating your data set by 1 point each time you do it, because eventually you don't, when you start off, right, there's no point before the first data point, right? So you can't really subtract anything that happened before, right? If you start with I plus 1, you can't subtract I from it. But I think this is a helpful concept because when you get to the lab and you plot your data, you have a bunch of position data. When you do your mathematical model, you'll end up needing acceleration. So you're probably going to have to take a derivative or two to get there, right? So just keep that in mind. Okay, so jumping into the fundamental, all right, sorry, before we do that, I also told you guys I would talk about exam, right? What are we doing for the exams? How is that going to work? For the exams, they're going to happen week 5 is the first one. What I want you guys to do is not come to class that day. If you're supposed to be there in person, don't. Everyone's going to take it at home. What you're going to do is you're going to zoom in to the class meeting, okay? You're going to zoom in with your laptop and your phone. Your laptop is going to be showing your face. Your phone will be showing your workspace, okay? And then you'll take the exam, right? And you'll have 2.5 hours to complete the exam and 30 minutes to upload it, right? So, you know, do it on scratch paper, take pictures of your work, and then upload it to the exam Dropbox, okay? The Dropbox closes at 3 hours after the exam starts. So if you miss that deadline, then unfortunately the exam doesn't get counted. For the exam, you are going to be allowed to use the master sheet that I posted on LoudCloud. Right? There's a big announcement post called Master Sheet, right? Please go through that. Please do your homework with it. Please get familiar with it because that's your sheet of notes for the exam. You'll be able to use that, nothing else. If you think that there's something that should be on there that's missing, let me know, and we can talk about it as a class and see if that's something that everybody wants me to add. Right now, I'll add it. But you know, let me know. Okay. You guys have any questions on the exams? Yeah, Danny, you could use a central difference if you wanted to as well. That's fine.
Would you mind repeating how we're going to take exams again? I'm sorry. I
Sure,
just
not
want to
a
make
problem.
sure like I'm 100% understand.
All right, so you're going to do it. I'm going to post the exam on LoudCloud. At the time of the exam, you will zoom in, right? It's a normal class time. You're going to zoom into this class meeting, right? For the TOS students, it doesn't change anything. For the in-person students, rather than have one half of you be in class and take it here, and the other half of you take it from your dorm room or your apartment or wherever you are, everyone's just going to take it at home on Zoom. What you're going to do is you're going to join the meeting with both your phone, because there's a Zoom app that you should download, or you can do it through the link, right? So join with both your phone and your computer. Your computer will show your picture, right? Picture of you taking the exam, sitting in front of your computer, and your camera, your phone or your other camera will be pointing at your workspace to show me that your workspace is clear of other distractions and other such things, right? And then I will sit in my office and I will watch the Zoom meeting like a security guard in a bad movie, right? That's my plan. And so you guys will just sit there on mute and take your exam, basically. All right. When you're done with the exam, you sign off of Zoom, you take pictures of your work, you upload it to the exam Dropbox, right? You will get a total of 3 hours from start to finish your exam and upload it. So you get 2.5 hours. The plan is for 2.5 hours of actual exam time and 30 minutes for you to scan it and upload it, right? That's the plan, all right?
And then if we have questions, is it just like we should message you
Yeah, if you
through
have
the chat or
questions,
whatever, and
chat.
you'll like have a breakout room like to answer our specific questions so we don't distract other students?
Correct. Yeah,
Okay,
so-
thank you.
Yep, no problem. All right. All right, any other questions with exams?
By work place, do you mean our hands, like doing the exam?
Like, I want to see like you and your computer and like your desk area. So yeah, like if it's just your hands, like working on the exam, that's fine. But I really want to see like you sitting there, right? The whole, I don't think that there's going to be people messing about, but I want to make sure that there's no messing about.
So if we all have our second cameras pointed at our work and at our like screens the other direction, wouldn't the rest of us in the call be able to just go look at what other people are doing?
So I see what you're saying. Yes. Don't have it on your, like, I don't want it on your exam work, right? I don't want to see what you're writing. I just want to see that the area that you're working in is just you, your computer, and a calculator, and that's it, and whatever paper you're using.
Like, can I put my phone like to the side? Sorry about this is kind of ridiculous, but
No, it's fine. It's important to get it. Yeah, so let's put your phone over to the side, right?
to the side, and you just see me like writing, because I don't really have a way to put a camera like behind me.
No, it doesn't have to be over the shoulder. I just want to see that your workspace is just the exam paper, right? That's what I'm going for, right?
Okay.
Okay. Cool. All right. Anything else? All right. Okay. So let's jump in, right? Here's some fundamentals, right? So mechanical systems, right? This is where we're living for the next like week or so here. I believe these to be the most intuitive of all of the system models, right? It's part of the reason why I went into mechanical engineering. I can see, like if I push on something, I can see how it reacts, right? Okay. Models for this are derived applying Newton's second, right? So sum of the forces is equal to mass times acceleration. Yes, Cody, only the master sheet that's posted. All right. So we're going to use sum of the forces is equal to mass times acceleration, but we'll probably stop calling it acceleration and start calling it double dot, x double dot, y double dot, or z double dot, whatever your favorite variable is. Okay. You apply F equals ma, Newton's second law, to each of the masses in a mechanical system, right? A mechanical system possesses the following fundamental characteristics. We have inertia, stiffness, and energy dissipation, right? So inertia is, in a translational system, it's our mass, right? It's a force or a torque that's required to accelerate our body, right? If I want to move a mass, I need to push with a certain amount of force and able to do it, right? Stiffness is basically our spring elements, right? They don't necessarily need to be springs, right? We have stiffness as a property of materials, right? So it doesn't necessarily need to be spring, but it's this property of being spring-like, being able to store and release energy. And then we have energy dissipation, right? So motion in a resistive medium, right? And so for us, what we're going to consider this to be is our damping, right? And we're going to, this is basically a viscous friction, right? And that's to say that we can treat viscous friction as a linear quantity. It's just B, which B or C, whatever textbook you're using, B or C, which is our damping constant, and that's multiplied by X dot, right? That's our force. We'll go over the element equations in a second, though. So a mechanical system can be modeled with three basic elements, right? Inertia, stiffness, and friction, right? Or damping, right? Okay. Cool. So let's get into inertia elements, right? Inertia elements include masses for translational systems and moments of inertia, which we're going to call J for rotational systems. You can see J or I get used interchangeably, right? J or I. The moment of inertia in general is the integral of r squared dm. These are, if you guys remember from ESG-360, when we derive some of these by hand, right? These are a pain to derive by hand. They're not necessarily difficult, but they can be time consuming. For the most part, what we'll do is if you need one, you'll either look it up in the table or you'll be given a specific moment of inertia, right? For a uniform disk with a radius of capital R, J is equal to 1/2 m capital R squared, right? Okay. And that's fine, right? These are basically based off of geometry, right? And so different shapes have different moments of inertia. Inertia elements can store potential energy due to position in a gravitational field and kinetic energy, right? Potential energy is mass times gravity times the change in height from some datum. And kinetic energy is either 1/2 mv squared or x dot squared and 1/2 j theta dot squared for rotational systems. And you guys may recall this from ESG-360, but energy is a scalar, right? Energy is a scalar. So what does that mean for us? Well, that means that we can just add all the different kinds of energy together, right? Because we don't care about direction, we just care about amount, which is kind of true, not really. We're not going to do too much with energy methods per se outright, but we will use them somewhat. So that's inertia. Is everybody all right with inertial elements? Have any questions about that? Doing okay. All right. I guess we're so far so good. Saying to my other class yesterday, it's really weird being in a classroom where there's absolutely no other noise. Like there's not even other people breathing. Very, very strange. It's like dead quiet in here. All right, so that's inertia, right? What about stiffness? When a mechanical element stores energy because it's been deformed, right? So if I bend the bar, right, as long as I don't bend it too far, it'll snap back, right? This can be modeled as a stiffness. Think of a diving board, right? Diving board isn't a spring, but it has some stiffness that allows you to spring it, right? You're storing some energy in the deflection, and then it releases as it comes back, right? Linear spring, it can be modeled by a stiffness element if it has some energy, storing energy due to deformation, right? So linear spring constant for translational systems and a torsional spring constant for rotational systems, right? And not confusingly at all, whether you're using translational or rotational systems, the spring constant is K, right? So that's not confusing at all, whether it's a translational or a rotational spring. You'll notice that I will write, if I have a mixed system that is both rotational and translational, I will call out K __ rotational or rot, just to keep the bookkeeping simple, but you guys can do what you like. The equation that governs a spring element, right? A stiffness element is Hooke's law, right? F equals Kx. Now, we've got force, we've got displacement from equilibrium. This is an important distinction that we're going to make in this class. We are going to assume that we are starting our system at some equilibrium point, right? Typically, the spring will be unstretched, right, at equilibrium, but it doesn't always have to be. Right? And we've got the spring constant. And guess what? If you do the units here, right, we've got K is in Newton per meter, X should be in meter, right, and then you're left with newtons. Right? That's a spring element, right? There are different kinds, right? Sometimes you will have a spring that is connected to two things that are moving, right? So both ends are moving. Now imagine that you've got two blocks connecting a single spring, right? I can move each one of these independently, right? I don't have to have them, move in the same direction. So how do we determine what the stiffness force is, right? The spring force is for something that doesn't have fixed ends, right? Something that is a free-ended spring. Well, you need to use the relative displacement, right? So if you'll notice here, right, I've got a spring, both ends are moving, right? I've got some input X1 here, I've got some output X2, right? So these two are not the same. They are called out as being different. One is X1 and one is X2. I am pulling on this, I have this spring and it is in tension, right? My forces are pointing outward here. So I need to do this as a function of the relative displacement, right? So the total amount that this spring displaces is X2 minus X1 in tension. What if it was in compression? Well, it'd be X1 minus X2, right? So just flipping the sign. It's important that when you do your free body diagrams and you write your equations, that it doesn't matter if you assume that your spring is in tension or compression, right? The math will work itself out in the end, but you need to make sure that you're understanding what that means for the relative displacement value, this X2 minus X1 or X1 minus X2, okay? So think about it when you're doing it. We'll do a bunch of examples where we kind of go through this. So far, so good. Everybody are doing all right. Maybe. Maybe not. Cycling through everybody's pictures. You guys all look super excited right now. I know this is really exciting stuff. All right. What about torsional stiffness?
Professor, can I, are you okay if I put like zoom on my computer screen so it's bigger so I can actually see the presentation bigger, but have my camera on my phone? I don't have a desktop camera yet.
Quinn, I'm not sure what you're talking about right now.
Like I'm giving the presentation.
He's saying yes.
Do what you got to do, man. Do what you got to do. All right. Okay, so that is a linear spring. What about a torsional spring, right? And again, it doesn't have to be a spring, right? We have a picture here of a bar that's embedded in the wall and we're torquing one end of it, right? Again, from materials, right? We know that if we don't surpass a certain limit, then we will not permanently deform, right? We will snap back, right? It's the same idea as a spring, right? So for an ideal spring, right, an ideal torsional spring, the torque displacement relationship is T is equal to K theta, right? So I don't want you guys to get confused because this messes with a lot of people's heads. People are fine when we talk about translation, right? F equals KX, right? A translational system and a rotational system are the same. The only difference is that one is translating and one is rotating, right? One moves in a straight line or in an arc, or right, and the other one spins, right? That's the difference. Mathematically, the only difference here is that instead of a force, we have a torque, and instead of a position, we have an angle, right? These are analogies that come across, right? The process of solving these two systems is the same, right? From a modeling point of view, there is no difference between, the only difference is the variable name, right? There's no difference between the quantity of a torque and a force from a modeling perspective. From a modeling perspective, I understand that physically these two things are much different concepts, right? But from a modeling perspective, these things are just variables, right? So we have torque, we have angular displacement, and we have our torsional spring constant, which, as I said earlier, is not confusing at all, right? Which is why I said is not confusing at all, because K is always K, right? And if you have a mixed system, then just make sure that you know which one is which, right?
Hey, Professor, real fast, under your K, your torsional spring constant, that's Newton meters per radian, not that minus sign is like Newton minus.
No, that's multiplied, right? It's multiplied. And that's actually an important point to bring up too, right? These are in radians. You want to be working in radians for the things that we're going to do. It's not super important in the beginning of the class, but it's going to be pretty important when we get to frequency domain analyses. We always want to be in radians. Make sure your calculator is in radians. Make sure your calculator is in radians. Okay, so we talked about this a little bit, but when we're talking about stiffness elements, they don't necessarily have to be springs. Materials have stiffness properties. They have spring-like properties. You can store energy in a material, right, by deforming it. And as long as you don't deform it too much, then you didn't break the system, right? Here are some translational, or as sometimes people call them, linear springs. I would say they call them that incorrectly because they are translational springs. If you want to figure out what K is, and you have all the measurements of the spring, right, you can figure it out for a coiled round wire spring. where D is the diameter, right? R is, G is the, well, D is the wire diameter, G is the shear modulus of elasticity, N is the number of coils, and R is the coil radius, right? So, you know, normally this is the point in class where I dump a bunch of springs on your table, right? And you guys get your calipers out and you figure out what all the spring constants are for the different ones, right? No, so that's not a fun activity. Nobody wants to do that. It's boring. What about if I had a rod or a shaft in tension or compression and I wanted to figure out the stiffness? Well, I can do that with this equation, right? The stiffness of a rod or a shaft is based off of Young's modulus of elasticity times the cross-sectional area divided by the length, right? Young's modulus is a material property. It depends on what we've made our shaft out of. Depends on how big the shaft is and how long the shaft is, right? That's what determines our stiffness, right? That's what determines our stiffness. Should be noted that I am not going to have you guys use that top equation ever, just so you're aware. So that's a for your information. That's not, the point of this class is not for me to see if you can plug and chug diameters and radii. That's not it. So here are some torsional springs. They look a lot like translational springs. Well, they're not necessarily torsional. I just found a picture of springs, guys. I apologize. I got lazy and I didn't actually look for it. All right, so how do we find it? Well, we can use a similar equation here to determine the spring constant for a torsional spring, which is for a round wire coiled spring, right? What happens if we have a rod or a shaft in torsion? Well, then K is pi d to the fourth G over 32L, right? Where D is the diameter of the rod, L is the length, G is our shear modulus, and D is the diameter of the rod.
Are we using all of these?
What's up?
Are we using all of these?
Probably not. Again, this is more of a for your information thing here. All right, coiled square wire springs and torsion. Right. So there are different types of springs. You can have square wire, round wire. I have some really weird ones if you go online and look for them. But, right. The important thing to remember about springs or about stiffness elements is that they don't necessarily have to be springs, right? And as long as something has an ability to hold energy due to deformation, it has the ability to hold a spring force or have some stiffness element, stiffness associated with it. That's the important part. Okay. You guys have any questions on stiffness elements? I use the term stiffness and spring force interchangeably, so we'll pick. I don't want it to be confusing, but that's in my mind they're the same thing. So I do use those interchangeably, just so you guys are aware. We good? Maybe not. Just keep going. Go faster, right? Go faster. I'm not going fast enough. Is that? Okay, cool. So let's talk about friction elements, right? Or for mechanical systems, what we're going to call dampers, right? So when a mechanical system dissipates energy due to friction, it can be modeled as a damper or a dashpot. Here we have a picture of what traditionally a damper looks like. The most common example that I can give you of a damper is if anybody has ever been in a house with a screen door, the part that stops it from slamming, right? That's a damper, right? What's the fluid that's inside of that? Well, it's just air. And I don't know if any of you have ever messed with one, but the way that you tune the damping in that is by, screwing or unscrewing a screw at the end that opens up or closes the orifice that the air is coming out of, right? Friction or damper elements provide energy dissipative forces when relative motion exists between two bodies, right? So this, you can see here, this is for right here, right? This is for a free end damper. Now, are all dampers free ended? Not necessarily. It's the same deal with springs, right? You could have a fixed end damper, you could have a free end damper. If it has free ends, then we have to take into account the relative velocity of the damper, right? So that's an important distinction here, right? So again, you can see here there's forces pulling on both ends here, right? And so the total damping force is B, our damping friction coefficient, times the quantity of x dot 2 minus x dot 1. So how fast is the damper itself moving based off of how the endpoints are moving. Right? We have an ideal linear damper. The relationship, right, is given by that equation that I just talked about, where F is my force, typically in Newton. X dot 2 minus x dot 1 is the relative velocity of the piston. And B is the viscous friction coefficient in Newton second per meter. And again, if my velocity is in meters per second and I multiply it times Newton second per meter, right, I'm left with newtons, and everybody's happy, and the units check and we go home. Okay. Now,
Question?
yeah, go for it.
So in that free body diagram, so we have the equation for force right there, and then we have a forward and backward force, both labeled F. We are saying that both of those F's are represented by this equation.
So yeah, essentially, yes. Right, because it's a tension force. A tensile force. Question. Okay. Anybody else? Any other questions?
Would there be a time that the forces on both sides of the linear damper be different? Like F1 is different from F2, or they're always going to be the same?
No, because this is just showing that the damper is in tension, right? That's all. It's like when we have a spring, right? If we had a spring and we were pulling on both ends, right, you wouldn't have, well, you could have. All right, so let's say it this way. Most of the time, those forces will be the same. If they're different, they will be given different subscripts, right? Like you'll be told this is F1 and this is F2, okay? Most of the time, that's a tensile force, and that's just us pulling apart, right, with a constant force on each end. Let's talk about this idea of an ideal damper and an ideal spring, right? What does that mean? Well, if we have an ideal damper or spring, that means that it doesn't do anything other than be a damper or a spring, right? There's no mass associated with it. There's only damping associated with an ideal damper. There's no stiffness associated with an ideal damper. There's only damping associated with this. Is this true in real life? Not necessarily, right? Not necessarily. But for analysis purposes, we are going to be using this concept of ideal linear dampers and ideal linear springs. Okay. What if I have something in torsion, right? For an ideal torsional damper, well, it's the same equation. It's the same equation, but instead of force, we have torque. Instead of velocity, we have omega. Omega is my angular velocity, right? Which I'm also going to call theta dot, right? So this is what I'm left with here, right? So as with a spring element, the damper element is a generic method for modeling friction in a mechanical system. It doesn't have to represent a physical piston, cylinder, dashpot, right? Something can have damping properties without actually being a damper, right? It just means that there's some energy dissipation that is occurring, right? What's an example of this, right? What's an example of this? Anything that moves in air, right? There's always wind resistance. Wind resistance can be modeled as a damping element, right? If you have a thin film of oil, right, we consider that to be a viscous friction element, right? So there's different, essentially, if you are taking into account some of the fluid mechanics of the system, right, typically via lubrication, we have some damping element that we can model. Let's get more into ideal, right? I jumped the gun. An ideal spring has no mass or friction, and an ideal damper has no mass or stiffness. It just does the one thing, right? So therefore, the inertia, stiffness, and friction characteristics of a mechanical system are lumped into their respective elements, right? Friction can involve a nonlinear relationship between force and velocity. Right? So we've got dry friction and square law friction or aerodynamic drag, right? These are nonlinear frictions, right? But so what are we going to do? Well, right now we're going to ignore them. We're going to learn how to handle them. Not today. We are going to talk about linearization and what that means, right? But for right now, if we have something that's nonlinear, we're going to assume that it's not a big deal, and we're not going to talk about dry friction. We're not going to talk about aerodynamic drag for right now. Here's some pictures of actual dampers, right? We've got various types. We've got rotary fluid dampers here in A. We've got, you know, traditional pneumatic line dampers, right? These look like those dash pots that we had. This is more in line with your your screen door damper, right? And then you've got heavy duty shock absorbers, right? Shock absorbers are dampers, right? They're dampers and springs together, really, but they just, right, they work in concert. And you'll notice, right, that we hardly ever just have a damper. Right, we hardly ever just have a damper. The reason your screen door has a damper is because the spring is going to be too forceful. It's going to slam your door, right? So we don't want the door to slam. So we put a damper on it to slow it down, right? Because the more force I try to push through a damper, the more energy gets dissipated. Right? The more velocity I try to slam through there, right, the more force I have resisting. It's based on our equation. All right. Anybody have any questions on dampers, masses, or springs? We'll get to it. We're going to do some example problems today, right? And I'm hoping that some of this will start to make a little more sense once we start getting into that, right? So I'm hoping. Everybody okay? All right. Cool. So let's talk about, and just in case you guys are wondering, that's when you hit it for the max boost. Anyway, let's talk about transformers. Right? And like I said at the beginning, no, it's not that kind of transformer. Right? What we're calling a mechanical transformer is a mechanical device that transforms a motion or a force. Right, so what do I mean by that? Well, it's either going to give us a force multiplication, or it's going to turn our translational force into a rotational torque, right? In this case of an ideal lever, right? Because it's ideal, there's no inertia associated with this lever, right? But what is a lever meant to do? A lever is meant to be a force multiplier, right? That's what we're doing. We're transforming our force. We're giving ourselves mechanical advantage, right? So if I have zero moment of inertia about my pivot point, right? So there's no moment of inertia about my pivot point because we've said that there's no inertia in an ideal lever. Well, then I just have F1 L1 times cosine theta is equal to F2 L2 cosine theta, right? Well, that's great, but it's got cosines, right? Well, the way that we handle this is we're going to say that most of our all of our systems are operating within a small perturbation window, right? We are disturbing the system a small amount. And for small angles, the cosine of theta is what? What's cosine of 0? That's right. See some people holding up
1.
1. It is 1. Cosine of theta, or cosine of 0 is 1. So for small angles, you'll be close to 1, right? For small changes in angle from my starting point, you will be close to 1, right? So we can change this to just F1L1 is equal, or negative F, not negative, sorry, F1L1 is equal to F2L2, right? And so depending on which one is our input and which one is our output, we can customize our length to get ourselves the maximum amount of force that we want out of a system, right? So we've transformed this force, right? We've transformed this force into something larger, or you could use it to decrease your force as well, right? There's no reason why you couldn't. Okay. So that's an ideal lever, right? Anybody have any questions on levers? There's definitely a homework problem that has lever. Guaranteed. Guaranteed. What about gears? What about gear trains? This is another kind of mechanical transformer. It's similar to, it's basically the rotational equivalent of the lever, right? We can use gears to gear up or gear down systems, right? I can get more torque out of a system or less torque out of a system depending on what my gear ratio is, right? So with an ideal gear train, which we have here, again, it's ideal. So there's no inertia associated with it, right? It's an ideal gear train. We're ignoring the effects or the fact that it has mass in the real world, right? We're ignoring that. We're going to talk about how to deal with unbalanced systems when we get the frequency response. But for right now, this is ideal. There's no mass associated with it. It works perfectly, right? The teeth always mesh. They're equally spaced, right? There's no flaws or defects associated. So if I have some input torque 1, that's going to create some omega 1, right? Some angular velocity, and everything's going to spin, right? And then if this top gear is spinning one way, the bottom gear has to spin the other way, right? Because that's how gears work. And so we create not only a change in our torque, right? The amount of torque we have, but we also have a change in direction, right? So we can define the idea of the gear ratio in a couple of ways, right? We can say that R2 over R1 is our gear ratio, right? The radius of gear 2 divided by the radius of gear 1, or we can say the number of teeth in gear 2 divided by the number of teeth in gear 1 is our gear ratio, right? We'll call that capital N, right? And we can use these ideas from dynamics, right? Where if I have something that's rotating about a fixed axis, I know that the tangential velocity at any point, specifically right here, I'm saying where these things mesh, right? Well, where do they mesh? So I'm saying right here, right? This is where V mesh is, right? So if you're looking at it from the side, right, you're going to have some tangential velocity here, right? And that tangential velocity is equal to R1 times omega 1, right? But it's also equal to R2 times omega 2 because these two things are touching, right? So they have to have the same velocity at that point, right? And it has to be in the same direction. Okay, great and good. So this is just R1 times omega 1, which is equal to R2 times omega 2. So I can rearrange that, and I can say, well, omega 1 over omega 2 is just equal to R2 over R1, which is just my gear ratio. So gear ratio is also a ratio of my angular velocities, right? Also that. Okay. But T times omega 1 is equal to T2. T1 times omega 1 is equal to T2 times omega 2. What is that? Well, that's the power on the first shaft. Has to be equal to the power on the second shaft. So again, we have this here, right? T1 over T2. We rearrange that. T1 over T2 is equal to omega 2 over omega 1. Right, which means that you can figure out what T2 is, right? This is a speed reducer, but you can figure out what T2 is by multiplying it by omega 1 over n, right? Omega 2 over omega 1 is just the inverse of my gear ratio. So I can figure out what my input torque is if I know the output torque. And I can figure out my output torque if I know the input torque and the gear ratio, right?
Question.
Yeah.
Okay, this might be a dumb one, but in your equations where you have n, is n just the variable for gear ratio, or is it meant to be like a,
So capital N is gear ratio.
okay,
Capital N is gear ratio. Lowercase n is number of teeth, right? So we have N1 teeth and N2 teeth. All right. You guys have any other questions, right? So gear trains, right? Ideal gear trains, they're perfect. They work perfectly. They always transmit. There's no losses, right? We know from thermodynamics that that's 100% the case. Thermodynamics wasn't a class where it spoiled everything for everybody and changed your life view. It's Ecclesiastes, the class. So let's talk about free body diagrams and kinetic diagrams. Right? This is going to be a little bit of hopefully a review from ESG-360. I know BMEs, I know you didn't take ESG-360, but you've seen free body diagrams before. Should be all right. Right? They do it, as far as I know, they still do it in physics, unless Doc McCarthy invented some new way of doing physics that I'm not McCarthyian physics. But anyway, so free body diagram and a kinetic diagram. Everybody is familiar with this concept of an FBD, a free body diagram, right? We're going to show all the forces acting on an object, right? But a kinetic diagram is slightly different, and we'll talk about that in a sec, right? So there's a few steps that we need to go through. I'm pretty sure actually Dr. Jones covers this with you guys as well, right? So the first step here is we're going to isolate the body of interest, right? This is why it's called a free body. You're going to take whatever you're interested in analyzing, and you're going to cut away everything else that is not that thing, right? We're going to isolate it. We're going to make it free, right? Okay, great. Step 2, draw your axes, right? What is your coordinate system? Are you using Cartesian, polar, path? Are you doing some really weird stuff that I don't even know about? Maybe, I don't know. Just make sure you draw it. Right? Look, mine's right here for this system, right? So I've done steps 1. I've isolated the body. The isolating of the body is just drawing this drum here, right? Step 2 was my coordinate axes. And notice I've also included my positive Z direction. How do I determine the positive Z direction, the positive rotation? I use the right-hand rule, right? Well, X into Y, and my thumb is pointing out of the screen, so that's got to be positive Z. That means positive rotations are going to curl with my hand, right, around the Z axis. That's going to be important when we're doing systems that rotate, right? Because that's how we're going to define, right-hand rule is how we're going to define positive and negative, right? Positive and negative. Step 3 is add in my applied forces. These are things like the weight, right? Weight, am I pushing on it, right? Is there a torque? Any applied forces get added in. Notice we have our weight down here. Step 4, replace any support with a force, right? So there's tension in this cable. That is not an applied force, right? That is tension. So we're just going to have that added on there. And then the final step here is to draw the appropriate dimensions, right? So my angles and distances. Notice I have some T, force T that is R away from my center of gravity, G here, right? And that's important, right? It's important because we need to know if this is contributing to any rotation. And because it's not going through the center for a rigid body, we know that this is going to create a torque. The force T is going to cause this to rotate as well as translate if it's not pinned in the center, right? So imagine this was a wheel that I had a cord around, right? And I just yanked up on this rope, right? It's going to start to roll, right? As well as move, right? Okay. All right, so if we follow these 5 steps, we'll have a very nice and beautiful free body diagrams, right? These are the important things that you want on here, right? What about a kinetic diagram? Well, all right. So when we're talking about free body diagrams, what are we graphically showing here? We're graphically showing the sum of the forces acting on this object, right? This is the sum of my forces. All of the forces that are acting on this are accounted for here, right? That's important because what we're trying to do with a free body diagram and a kinetic diagram is we're trying to graphically represent our equations of motion. And our equation of motion is Newton's second law here, right? And so how do we deal with the second part of that, the equals ma? That's our kinetic diagram. And so the first step is the same. We still isolate the body, right? I draw my circle. Then I draw in mass times acceleration of a particle or free body at the center of gravity, right? And I do this in the positive direction according to the axes that I have chosen, right? Because here's what happens. If you choose the negative direction, it's not wrong. The math will play out. But if you get a negative, that means you chose wrong. So if you chose negative and you get out a negative, that means you're actually moving in the positive direction. Whereas if you chose positive to start with, it's less confusing, right? Less confusing. All right. For rigid bodies, we also include the term I alpha, which is, as you can see below here, we've got sum of my forces is equal to mass times acceleration, or sum of my moments about the center of gravity is equal to I bar alpha, and I bar is J, right? It's my mass moment of inertia taken about the center of gravity. These look a lot like, well, this one is obviously Newton's second law, but I can also write this as mx double dot, right? And I can say, well, this is my double dot, and this is equal to mx double dot. And I can say that this is J theta double dot, right? I can say those things if I want. In fact, I will say those things. So what's the point, right? Is it really necessary to draw a KD every single time that we do a problem? You will notice that in practice, people don't typically draw KDs. Full stop. They don't. I like to teach you guys to do it because you have a full graphical representation here of my 2 equations. So if you did this diagram correctly, right, and included everything, you would always get the right equation, right? Because you have everything on this picture that you need to write these 2 equations. Right? Now you remember, hopefully, that the Dr. D #1 super terrific 5-step problem solving method, right, is to draw the free body diagram first, right? And that's intentional because I want you guys to you should always be drawing a picture. And I know I harp on it and we go over it over and over and over again in multiple classes, but that's because it is important. You guys have any questions on FBDs or KDs so far? We're doing all right. Maybe, maybe not. Well, let's try one then, right? Let's try one. We'll do this one together, and then I'll have you guys work on the next one on your own, okay? So we're going to draw a free body diagram and a kinetic diagram for this bar AB, or you can call it ACB, right, if you want, of the mass. It has mass M, known force P is applied at the bottom of the bar. Okay? So there's a couple of things here, right? You're told that this has a known mass, right? So you can't ignore the mass because you know it, right? So if it has a mass, that also means that there's some weight, right? And you should probably put the weight at the center of gravity. We'll talk about that in a second. What's the first thing we're going to do? Well, step one was to isolate the body, right? So here it is. ABC or ACB, AB, whatever the bar is you're calling it.
Do you mind going back a slide real quick?
Which one? This one?
Yeah.
All right, so the first step is to isolate the body. So we just draw the bar, right? We just draw the bar. That's it. And the diagram's still down here, right? Anybody needs it. All right, so I isolated the body. Notice when I isolated the body, what happened? I no longer have this connection at C, right? That is gone. Where it's connected to the wall is gone. It's gonna be important in a second. But first I'll draw my axes. For this, that's just gonna be X, Y, and positive rotation going from X to Y by the right-hand rule. Okay. Add in my applied forces. Those are things like P and the weight, right? So there we go. Replace my supports. What kind of supports do I have here? Do I have any supports?
Would it be C?
Right, at C. What is happening at C? What is, so I know, all right, so again, I know that the biomeds don't take statics and dynamics, right? Traditionally in the 360 class, but I know you have Dr. Jones teach you a little bit about it. One of the mechanical engineers or the BSc students, what kind of connection do we have at C?
A pin.
What was that?
A pin.
Yep, that's right, Danny, a pin. We have a pin connection. And what does a pin, what's special about a pin connection? What does it allow our system to do?
The pin connection allows free rotation with no translation.
Exactly. Free rotation and no translation. So basically you can rotate around point C, but you can't move point C up, down, left, or right, or in and out of the board, right? But I can spin around it. So that means I have reaction forces, right? Because something is holding that in place. And because I have reaction, something's holding it in place, I have to account for that with an X and Y reaction force, right? There's technically a Z reaction force too, but we're doing a two-dimensional problem, not a three-dimensional problem. So we don't have to really worry about that right now. Okay. Reaction forces are all about, am I opposing motion in a certain direction? If yes, then reaction force is necessary. If no, I don't have to put anything there. Right? That's what it's about. And then finally, put our dimensions in. Great success. A free body diagram has been completed, right? So what about the kinetic diagram? Right? Step 6, kinetic diagram, where we isolate the body and then we add in our inertial terms, right? And here we go. I could write all of my equations based off of this, right? This is equal. How did I know which direction this would be moving? Does this make sense? No, not really. I mean, intuitively, if I'm pushing on the bottom like that, I should be rotating the opposite way, right? But I always pick positive because the math will play it out. I always pick positive, the math will play it out. Guys have any questions? Not yet? All right. Well, now it's your guys' turn to do that. So, yeah.
Sorry. I was behind on writing. Can you just explain that kinetic diagram really quick?
Kinetic diagram. The kinetic diagram shows our inertial terms. And what I mean by that is the mass times the acceleration, right? So remember, what are we trying to do with this diagram? I'm trying to show sum of the forces is equal to m x double dot, or sum of my torques is equal to j theta double dot, okay? That's what I'm trying. This is the equation that I'm trying to build, right? So for something like this, well, I've got all my forces, right? And you would do this in the x and the y directions, or you could leave it as a vector, that's fine. But this is what we're trying to build, right? And so in order for me to do this, I need the equal sign to be my inertial components, right? It's mass times acceleration in the y, mass times acceleration in the x, and this system is also rotating, right? Again, we're describing how the center of gravity of this rigid body is moving, right? So this center of gravity is going to, as it rotates, as this entire thing rotates, right? Well, let's say it's going this way. It's going to follow a path that looks like that, right? It's going to use red. It's going to like follow this path-ish, right? Give me a circular path that it follows as it rotates around this point. Right? I'm pushing on the bottom, it's going to rotate. So this point in space has some acceleration in the x and some acceleration in the y every point along the way here, instantaneously. There's also some moment of inertia that describes the angular acceleration about that point G, which is I alpha. Now for this particular problem, I would say, I would scrap using the moment of inertia about point G, and I would use it about point C, but it doesn't really matter. You're just going to use parallel axis theorem. So the whole point of the kinetic diagram is so that you have a graphical representation, a complete graphical representation of Newton's second law. That's the whole point of it.
A quick question as to why you would put it at point C versus point G. You said the moment of inertia.
You're rotating about that pin, right? The whole system spins around the pin, so it's just a little bit cleaner. It doesn't matter. You can take the moment of inertia at any point that you want. It doesn't matter. But for most of our equations, we're going to be discussing what happens about the center of gravity of a specific rigid body, right? So that's what the bar means, right? And you have this thing here, it's I bar, right? This means that it's about the center of gravity. Okay. Any other questions? Watch that dynamics review. There's some good stuff in there, right? If you guys want to knock some rust off. All right, so I want you guys to try this one, right? You've got a drum of 4-inch radius that's attached to a disc of 8-inch radius. The combined drum and disc have a combined mass of 10 pounds. A cord is attached as shown, and a force of magnitude P is equal to 5 pounds is applied. The coefficient of static and kinetic friction between the wheel and the ground are mu sub s and mu sub k of 0.25 and 0.20 respectively. Just draw the FBD and the KD. I want you to draw the free body diagram and the kinetic diagram for this drum disc system. I'll give you guys a few minutes for that. All right. You guys want more time?
I got it.
Okay. Share it. Throw it up. You might have to take off your background, Danny, because paper eats the background.
Yeah, give me a sec. Sorry about this. Sorry, I don't know why I can't seem to just easily turn it off. Does anybody know
Where it says stop video, you hit the top arrow, hit choose virtual background, and then there's a none.
Stop video?
Go to choose. So on the video button, where it says stop video, there's an up carry.
Oh, I got it. Never mind, I got it. Yeah, that lets me choose the video background, but it doesn't let me turn it off.
So say no background is the very first option.
Is there no? Okay, I'm sorry. Wait.
You were in your room for a second, and now you're in the Northern Lights. There you go.
Should have written this bigger. I don't know if my webcam picks this up, but basically what I have is I broke down the two torques, one from the force and one from friction, and I applied them at their, I took the two forces, the force of friction and the force of the rope, and then I basically applied them at their distance from the radius to make two torques, and then I have basically fed those into the equations of motion. So, and then for my kinetic diagram, it's very simple. I have my acceleration in one direction. It's simply the difference between the torques divided by their conjoined moment arm. And then I have the torque is, the I alpha is equal to the difference of the torques, or the sum of the torques, depending on the direction of interest. And then I have two directions, y1 and y2, which could be x, y, x, z, whatever. And then I have a theta direction on my coordinate system. There's just some other stuff there, but I don't know if you can make it out.
Your rotational positive direction doesn't jive with your Cartesian coordinates there, right? Using right-hand rule.
Yeah, I think I wrote the axis backwards.
Yeah, but otherwise,
my equations of motion are still true in the frame of reference that I've chosen, even though it's not a traditional frame of reference.
Cool. So.
Yeah, so don't do what I did. Use normal coordinates.
All right. Cool. Thanks, Danny.
No problem.
So, right, here's our system. We isolate the body, right? There we go. Draw our axes, right? Again, the real thing that you want to make sure you're doing is the right-hand rule, right? Make sure that the right-hand rule is being followed. It's just going to make things a lot easier and a lot cleaner. We put our applied forces. So I've got the weight. That weight is the total combined weight of the drum and the disc together. Their center of gravity overlaps, right? Because it's a disc on a drum or a drum on a disc, and they have the same axis that they're rotating about. So their center of gravity is aligned. So you can just add the two masses, right? And get that total weight added there. Then I've got, my applied force P here. I need my supports. Don't forget normal force, right? It's touching the ground. The ground is touching back, right? There has to be a normal force. Yeah, Cody, that is correct. Cody Young, the wheel will roll on the ground in the direction of rotation.
Could you explain why the friction?
Cody Wood, I don't think I understand your question. Why would rotation be opposite of what makes sense? Was that asked to me or?
Yeah. So like in our previous example, when we first did it with the wheels,
Yeah.
we had torque going up on the left side of the wheel, and our rotation was still in the same direction as this problem. But wouldn't
Right.
that be backwards?
So I
So the
just
first problem.
So this is just showing what is the sense of positive, right? So if it's going the other way, it's just going negative. I'm just trying to remind myself that if it's translating to the right, that's going to be a positive. And if it's moving off of the ground, that's going to be positive. It's moving up. Or if it's rotating counterclockwise, right? Counterclockwise is always a positive rotation in this sense, okay? So it's not indicating necessarily what direction it's moving in. It's just telling us what direction we consider to be positive. Because when we go to write our equations, we need to know whether we have something that's positive or negative, right? Because sign errors count, right? Sign errors are gonna get some points off. They're not gonna kill your entire thing, but you'll lose like half a point here, half a point there for sign errors.
Okay.
Throw our dimensions on, right? I know the radii of my two discs. My kinetic diagram is this, and it's not wrong. It's also not wrong to say that that's 0, because why? Because it's on the ground, and we're gonna assume that it's rolling on the ground and that it doesn't. We weren't told that it hits a sick jump or anything like that, right? So there's probably no acceleration off of the ground, right? Guys have any other questions on FBDs and KDs?
So when we were like told for the frictions, right, we had our static and kinetic. If we're given to that and we're like drawing our free body diagram, we'll have to just group those together and like all that stuff like we were doing on the free body one right here. We just say like the friction is in one direction.
I'm sorry, Carl. I'm having a little trouble hearing you.
Sorry. Yeah. What I meant to ask is like for the frictions, right? Like we could just put an F and that represents friction, or do we have to like do a whole thing?
Yeah, and that's fine for this in particular. The reason I put friction on is because it calls specific attention to dry friction in the problem statement. For the problems that we're doing, like I said earlier, we are going to summarily be ignoring dry friction for now. Remember, friction is one of those forces where it is important that you draw it in the right direction. So think about what way this is moving, right? If I'm pulling this up at P, that's going to cause a rotation that's counterclockwise, right? But it's also going to cause what? How is this going to move? Well, it's going to start moving to the left when I pull there, right? It's going to start rolling to the left. It's going to move to the left. And so friction is going to oppose my motion, right? So just keep that in mind.
I
have a question.
Oh, never mind.
If that was slipping, like if it was spinning in place, would the friction be pointing left?
So that's coefficient of dynamic friction. If it's slipping.
Right. So talking about slip conditions, right? That's why we were given the different coefficients, right? So if it's kinetic, if you have slipping, then you're gonna use kinetic friction, not static friction.
But would that be pointing to the left?
Yes, would, if it's slipping. You're
right. Just question about the frictions real quick. Are we consolidating them in that singular F point, or are we just neglecting the friction between the wheel and the drum?
So, Sean, I'm having a little trouble hearing you. Can you?
Oh, sorry. I'll get closer to wherever the microphone is.
That works. That's working.
Okay. So for the F point, are we just consolidating the two, or are we neglecting the friction between the drum and the wheel itself?
So for the friction, we are just doing the friction between the ground and the disc, right? We're assuming that there is we weren't told about any friction between the drum and the disc. So we're just talking about between the ground there. That's why we put it there. When we start walking through a couple of problems in a little bit, we're going to see that we're not going to talk about dry friction at all. We're just going to talk about damping and viscous friction, and we're going to use our damping equation and our damping elements. Cool. Anything else?
Question.
Yeah, Matt.
So that force upward at P, is that going to create a torque that we draw on the free body diagram at point G?
So if you draw it as a torque, you get rid of the force, right? It's one or the other. It does create a torque. I would leave it as the force, right? Because when you go to write your equations of motion, you have a force there, but that force also contributes to the torques, right? So you don't want to forget about it. So personally, I would leave all of these drawn as forces unless you're told specifically that you are given an applied torque, right?
Okay.
In some cases, that's, you'll just be given an applied torque, right? So.
Gotcha. Okay.
Cool. Question. You guys are on the ball with these questions today.
Can you show what you were doing with the right hand rule? Because I've seen with the fingers and using your hands, so I want to see what you were doing.
Okay. So this might look backwards here, right? So put your fingers in the direction of X, right? Okay. Then curl your fingers in the direction of Y, right? Of positive Y. My thumb should now be pointing away from my computer screen. Yes, everybody? That's positive Z, right? So that means that X is positive to the right, Y is positive up, Z is coming out of the board. Now, because of that, I've curled my fingers towards Y, right? So that means positive rotations are going to be counterclockwise. All right, so let's do the same thing, right? Imagine you're on the y-axis, right? I put my right hand along the positive y-axis and I curl it into the z. Now I've got positive x, right? I'm in the same direction as positive x now. That means that positive rotations are going to be going from y to z, right? So if you ever get confused, put your fingers along the direction of one of the axes, curl it into the other, and your thumb will always be pointing orthogonal to the two of them, right? Which is essentially what a cross product does. It's going to be 90 degrees to both, right? So in 3D, right, we end up with something that looks like this, right? And if we remember, right, I, J, K, this is something that I am a big fan of, thanks to Dr. Michael Paolino in Lafayette College. This is the way he taught us how to do cross products, right? The sense of a cross product, I cross J is positive K, J cross K is positive I, right? So if you go counterclockwise in this circle that I just drew up here, right? If I'm taking the cross product of I with J, that will give me positive K, right? X direction, Y direction gives me positive Z, right? So when you do the right hand rule, you're just really doing cross products. What if you go the other way, right? Well, I cross K gives me a negative J, right? So we're not going to be too heavy on cross products in this class, but that's always a good thing to remember. And the way that coordinate systems are made is really just from doing cross products, right? Which we hopefully remember. And if not, right hand rule exists.
So when we're doing, go ahead, you're good.
Okay, we're using this rule to find the axes. So how do you said, like, so if we're putting our fingers in the direction of X, but we don't know the X because we're the ones that have to design the coordinate system, is that because it's rolling in that direction? So we know that's where X is? I'm asking how you use the rule to make that axis. Does that make sense?
Completely arbitrary.
You pick it wherever you want it to be.
Got it.
I can have a coordinate system that looks like, as long as these two things are 90 degrees apart, it doesn't matter, right? For Cartesian coordinates. I mean, this would be not very fun for you to use for this particular problem, right? But this is the same reason why when we do blocks on inclined planes, we can angle this however we want and put it in whatever direction we want, right? So the right-hand rule for this would be X into Y. Z is still coming out of the board, right? So what happens if I draw this blue one where I've got Y this way and X coming down? Well, X into Y, Z is now positive into the board, right? So you can choose you can choose whatever X, Y, and Z whatever X and Y you want, however you want to orient them, but your positive rotation is defined by the right-hand rule, right? Your third axis is always 90 degrees to both of those axes for Cartesian coordinates. Okay.
Thanks.
Yep. Cool. Any other, Kat, did you have something?
Yeah, I just had a mini question, I think. So for the fingers towards the X, just like is it always palm up, whichever way the X is going?
Not always. It depends on, well, yeah, I guess it is always palm up. Yeah. Yeah.
It's just a counterclockwise rotation and then a counterclockwise rotation until you get 3 axes. The left-hand rule is clockwise rotation until you get 3 axes.
So yeah. So if you go palm up every time with your right hand along X, and you curl into Y, right? Because if you don't go palm up, so we'll use the blue one again, right? If I don't use palm up and I try to curl into, I'm gonna break my hand. So don't break your hand. It's not worth it. It's not.
Right. And then when we're doing the free body and kinetic diagrams, do you want us to include the Z direction in the coordinates at all, or we don't, it's not necessary?
You don't need to include the Z direction, but you do need to include the positive sense for rotation. That's important.
Gotcha. Thank you.
Anything else? All right. Let's talk about translational mechanical systems. Let's talk about them, right? Here are the super terrific #1 5-step method for developing models again, right? Okay, cool, cool. Just to review from last class, right? We just went over how to do an FBD and a KD, right? We just did that. Hopefully we're good. If you guys are still having issues with it, come to office hours, ask questions, make sure, because it's really important. It's how we're gonna base everything off of here, right? So remember, we're gonna draw a picture, we're gonna identify inputs and outputs, we are going to identify our mathematical truths, we're gonna reduce our equations, and we're gonna evaluate solutions, right? Now, I said this, and I don't remember if I just said it in the last class, but I'll say it again to everybody. You can kind of consider this the rubric by which I will grade all of the assignments. Any problem that you do, I'm going to basically grade it using this rubric. Okay. So to maximize the number of points that you get, you should do the things on this list. Okay. You'll see that when I do the problems, when we start going through some examples and I do the first one, right, you'll see I follow this basically to the letter. I would highly recommend that you do the same just until you get your feet under you and you feel confident with what you're doing. I'm hoping that you guys can build some muscle memory, and then in stressful situations, you won't freak out. That's what I'm hoping. So let's look at this. Let's look at this thing, right? We're actually doing an example, right? I'm gonna stop talking, right? So I've got a high-speed solenoid actuator valve system, right? Here it is, beautiful system. We want to derive the mathematical model or the equations of motion for this, right? So I've got this electrical input, right? And I've got, so this seems intense, right? I've got displacement positive to the right, measured from the seated position. I've got an electromagnetic force that pulls the armature towards the center of the coil and closes the air gap. And I've got a return spring. So for those of you who are not familiar with solenoids, what does a solenoid do? It's an electromechanical device that's typically used in valve systems. It's not only used in valve systems, but that's where we typically see them. And what it does is it generates an electromagnetic force that pulls a pin away from something, right? And then when the force isn't there, the spring brings it back. Another application for this would be locking mechanisms, right? Hotel doors use solenoid valves for locking. All right, so quick question. Who is intimidated by the schematic that we just saw for that model? Be honest. All right. I mean, that's a beastie, right? But can we do anything to simplify that, right? Well, sure we can. We're gonna simplify it. So how do we How do we do that? Well, first of all, we're going to use a lumped model. Remember, we talked about lumped models last class. That's where we take all of our elements and we define them by their simplest form, right? So we're going to lump the armature and the spool valve into a single mass, right? So we'll have a mass, M. We're going to model the return spring with an ideal spring, which will have a stiffness of K. And we're going to model the friction due to the hydraulic fluid as an ideal damper with coefficient B, right? And then we're going to redraw it. So when we redraw this, we end up with something that looks like this. I've got some electromagnetic force, right? I've got some spring and I've got some damper. Now notice it's attached to the ground here, right, on the right-hand side. But this mass is just the armature and the spool valve together. This is my hydraulic fluid, that B, and this is the dynamics due to my return spring. Right? We didn't even touch what FEM looks like. We'll do that week 3. We'll talk about electromagnetic force. Right? Talk about that week. Right? So that looks a lot more manageable, right? Wouldn't you say? Maybe, maybe not. I think that looks more manageable. The other one was gross. The other one was gross. Okay. So now that we have our simplified model, we'll apply Dr. D's 5 steps to this, right? So first step is what? Well, it's a free body diagram, right? Now, you guys are going to be amazed at this, my skills of an artist here. Boom, there's my system. There's my mass. I know, right? We were told in the problem statement that this was positive in the X direction, right? This was being moved in that direction. Okay, I'm going to draw my total coordinate system here, right? Is this necessary? Is this necessary? For this problem, is there any rotation associated with this? Is there any rotation associated with this?
No.
No, it's a pure translation, right? This is going to slide back and forth. So we don't really need the full coordinate system. This is just going to move left or right. So it is enough for this particular problem to just say, I know X is positive to the right. I've defined X positive to the right. Okay. Okay. What else do I have here? Well, I've got some electromagnetic force, right? If I'm moving this, so I want you guys to think about this, right? If I'm pushing on this to the right, okay, with my electromagnetic force, this is going to want to move to the right. So if you are looking at that spring, one side is connected to the wall and the other is connected to the mass, okay? So the first question is, do you think that this is a fixed end spring or a free end spring?
Fixed.
It's fixed, yes, right? One side is not moving and the other side is moving. That means that it is a fixed end spring. If both sides were moving, if this was in between two masses that were both moving, then we would have free ends. But because this is fixed end, we'll see that that has implications later, right? So that means that the damper has a fixed end as well, right? Because they're both connected to the same spots. Okay, awesome. So if I'm pushing this mass to the right, what direction does that mean? Does that mean my spring is in tension or in compression?
Compression.
It's compression, exactly, right? And if my spring is in compression, then it's going to return a force on this block like this, right? Because I'm squeezing the spring and the spring wants to push back out. So I've got a force on my mass, right? Due to that. What about my damper? Well, I'm also compressing my damper, right? And so my damper is also going to have F sub B. Okay. Another way of thinking about this is that if this is in fact a friction force, right? This is a viscous friction force, it better be opposing my motion, right?
So the F of B represents the fluid of the
Yes.
compressor. Okay.
Exactly. That's AG. All right. There's my free body diagram, right?
Since it's suspended in the fluid, or just assuming that we don't have to, since it's suspended in the fluid, are we assuming we don't have to worry about the gravitational forces, or is that just good?
So because the motion is in the X direction, we're not going to worry about gravitational forces for this particular problem. Because we're just trying to get the equation of motion in the X direction, right? We're going to assume, because we're assuming everything is ideal, we're going to assume there's no travel up or down, right? It's just going to be left and right. It's just going to be lateral motion. Good question. Okay. All right. So is everybody okay with this, right? That's step one. You just got a bunch of points for doing that, right? Okay. The next step is identify my inputs and my outputs. So I want to go back here, right? What is my input to this system? What's initiating my motion?
The electromagnetic force.
Yes, Scott, exactly. The electromagnetic force, right? What is it intended to produce? What is the output of this system? I apply the force and then something happens. What happens?
You get movement.
Yeah, you get a movement. The output is X, right? So my input is my electromagnetic force, and my output is X. Okay. That seems trivial, right? But we're going to see in a second why it's important to identify these. And specifically, later in class, it becomes really important. Okay. So we have some force. Because we applied a force, the system moves. That's simple, right? Okay. All right. Everybody's cool and sees where the inputs and outputs come from, right?
All right. Why is the output X?
Because you applied a force and it caused motion. It caused a change in displacement.
Displacement. Okay.
All right, so let's write down our mathematical truths. What are the equations that govern the system, right? Well, the big first one here, the big boy, right, is Newton's second law, right? F equals mx double dot. We have two other equations here. We know that our spring force is defined as kx, right? And this goes back to that question where you guys answered originally, which is this fixed or free end? Because it has a fixed end, it depends entirely on the motion of the block, right? There's no relative motion. One side is fixed and we're pushing against it, right? And we also have the damper force, right? And this comes from our other equation, Bx. Now, why didn't I write that in terms of A and V, right? Why didn't I write F equals ma and FB is equal to BV, right? For velocity. Remember, our output is X. So we want everything to be in terms of X, right? Acceleration is just the second derivative of the position. Velocity is just the first derivative of the position, right? We want to just have X. And there's a specific reason that we'll see when we get to Laplace transforms as to why we want X dot, X double dot, and X, right? But for right now, we want to live, right? I told you guys at the beginning of class, all physical systems can be written as ordinary differential equations, right? We're going to write this as a second order ordinary differential equation, right? Okay. So for basically the mathematical truths as they break down for a mechanical system comes down to three things, right? For this particular problem. We've got an inertia, right? I've got the equation that describes my inertia. I've got the equation that describes my stiffness. And I've got the equation that describes my damping. Okay. So I'm going to go back here. And
That, the x dot is x2 minus x1, right?
No. Remember, this is a fixed end, right? So if we go back to our schematic here, this side of K and this side of B are not moving. So technically, yes, it's x2 minus x1, but x1 is 0, right? Technically.
Okay.
But for a fixed, when something is fixed ends, it's just a function of x or x dot. If this were attached to, you know, like another mass over here, M2, then we would need to know how that's moving in order to get the appropriate, equations. And we'll talk about that too. I mean, we'll do lots of problems with free ends. There's a couple of nice ones in the homework. All right. So if we're looking at this free body diagram, right, the next step is to reduce my equations of motion, right? So I've got my free body diagram. I've got my inputs. I've got my outputs. I wrote down my mathematical truths. How do I chain all this together to actually get an equation of motion, right? Well, I can look here, right? Notice I didn't do my KD, right? The KD doesn't really help me to do most of this, right? If I wanted to do the KD, right, what would it be? It would just be there's no rotation, there's no y direction motion, right? This is the KD for this particular system. Okay. The free body diagram is infinitely more important, hands down, right? Hands down. If you guys only do one of these diagrams, do the FBD, right? If you're only going to do one, do the FBD, right? All right, so I've got all this stuff going on, right? I've got my inputs, outputs, I've got my FBDs, I've got my mathematical truths. So let's reduce our equation. So how do we do that? Well, I'll start with the sum of my forces is equal to the mass times acceleration, right? Well, what is the sum of my forces? What are all the forces acting on this body? Well, if we look back at our free body diagram, right, I have my electromagnetic force, which is acting in the positive direction, minus my spring force, minus my damping force. And that whole thing is equal to mx double dot, right? So that's just the sum of my forces, right? The sum of the forces acting on the body is equal to the mass times the acceleration. Okay. Well, using what I know, right, I'm going to do some algebra here, right? And I'm going to plug in for f of k, kx. And I'm going to plug in for f of b, bx dot. And that's going to equal mx double dot. And I think you guys might start to be seeing what's going to happen here, right? But remember, we're supposed to reduce this such that our inputs are on one side and our outputs are on the other. And if I do that, I'll end up having mx double dot plus bx dot plus kx is equal to my electromagnetic force. Equation of motion. Done. That is a second order, ordinary, linear differential equation. It's like the gold standard of all of the equations that we can have in this class, right? How do we know it's second order? Well, the highest order derivative is x double dot, right? Which is the second derivative. So that's what makes it second order. Can we evaluate this? Not yet, right? We'll get there. but we're not going to get there for a bit. We're going to focus on just how to set up all the equations first. You guys have any questions on this? Doing okay.
Why are they minus signs?
What's up?
Why are they minus signs?
Because they're negative, right?
Yeah.
Positive is to the right. So when I sum all these up, I've got FEM minus FK minus FB is equal to MX double dot, right?
Got it.
Also, these are not, we've made an assumption here that these are, I've drawn these offset, but they're not really offset, right? They're acting at the same point. It's just that if I drew them overlapping, nobody would be able to see them, right? So that's why there's no dimensions about where these are being applied, okay? Right now, we're assuming everything's moving through the center of gravity. Not going to do it. All right. So we're going to do time trials. So I'm going to put you in breakout rooms. We don't have 45 minutes, unfortunately. So I'm going to give you guys 20 minutes because that'll give us enough time to roll it up. It'll be fine. Don't worry. You guys will do great. No Chag, no computer, no text. Right. Well, I guess you have to use your computer. Otherwise, the Zoom call is going to be pretty short. You can use your notes and calculators, right? Points are given out per section, right? So the TOS section, you're competing against the other TOS section class groups for points, and the non-TOS, you're competing against the non-TOS for points. So there's like 11 teams. So if you are the first team in TOS to finish, you'll get the 8 points, right? And if you're the first team in non-TOS to finish, you will also get 8 points. Okay, great.
Is it like for participation for the week? Like if we get dead last, do we not get the 7 points for participation for the week?
You get the full participation. You just don't get the try. This is tri-quizzard points, Carl.
Okay, I just remember I saw on the participation week. It said 7 points out of 10 for the time trial.
Far more important than participation points. This is your tri-quizzard ranking that we're talking about here. All right, anyway. All right, so here's the problem, right? You guys are going to do this. Please write it down, take a screenshot, something so that you guys have it. I'm going to give you 20 minutes so we have enough time to talk it over. All right, so I've got a mechanical system shown here. It's composed of a single mass, a spring, and a damper. The vertical position of the mass X is measured from the undeflected position of the spring. I want you to derive a mathematical model for the system. Okay. I'll give you guys a couple seconds before I start up the breakout room so people can get everything broken down. Interesting. Why is everybody not in the... Did I lose a bunch of people? No, everybody's here. Weird. So apparently, it did not. Did everybody sign up with the same emails that they normally sign up with? All right, I'm gonna have to figure out what team everybody.
I didn't use my school email. If that impacts.
Whatever one.
What are we signing up for?
Whatever you registered for class with, I put you guys in based off of those. So I'm gonna have to reassign all of these based on what account you're using right now. It's fine. Don't worry about it. I got it. Probably going to see an Excel sheet now. Okay, are you guys still seeing the screen? Or are you seeing this Excel sheet? Probably this Excel sheet.
Nope, we see the main screen, the PowerPoint slide.
All right, good. Sorry, this is gonna take a second.
Do you want the time dependent or the space domain mathematical model?
Time dependent. Sorry. We'll get there. Supposed to be. Thought I took care of this earlier.
So these groups are then different from the groups that we were in
Nope, they're
on
the same
Tuesday?
ones. They're the same ones. It just didn't save for some reason, because that would have been ideal.
That would have made it.
I'm not salty about it. It's fine. I'm fine. Everybody's fine. Okay.
Didn't want to make it too easy on you, Dr. D.
Yeah, it's true. I'm almost done. I'm sorry. I apologize. I know this is exciting class time. And I promised I wouldn't pull a Dr. Williams. Yeah, no. But all right, there we go. Have a great time. I will, I'll bounce around. You guys get 20 minutes, all right? All right, everyone's in breakout rooms. This is going to be really exciting, I know, for y'all watching on YouTube. Especially when I start bouncing around to the other breakout rooms. Wah wah. They are so close. They're all doing the thing though, where they forget about preload. That's it. And when I say they, I mean you. We're all forgetting about preload. Don't forget about preload, please. Please. All right, I'm gonna go check on some more.
Are we the only ones in here?
Looks like it.
Wow, are we gonna get some points?
Sweet.
We got it. Either we're really wrong or we're really right. All right. This is cool.
We didn't have to. No, we
left our other
couldn't.
guy. What was his name?
Do it.
Do it. We gotta go get him. I'm gonna go back in the breakout room.
You're gonna? Yeah, he's gonna. You're on mute, by the way.
Can we go?
For some reason, you're on mute again.
Sorry, that's weird. Okay. Did they go back in the breakout room?
Yeah.
How do you do that?
If you look at the bottom, like next to share screen, it says breakout rooms, and it gives you the option to go back into it.
Oh. Oh, I didn't know that. That's cool.
But they're coming back.
There's a timer in the waiting room, and we still got 6 minutes left in the breakout room.
Oh. Well, then how does he know who finished first?
Oh yeah, that's cool. We can just wait in here too, but
Yeah, we'll just be like, yeah, we get it.
Why did I close my? I guess we're live on YouTube, guys.
Ooh. Oh, that's true. I didn't think about that.
Is he on YouTube? I'm gonna look for him. Let's see.
Check too.
You have to go through the Loud Cloud.
That smells really.
I don't think he's live right now, is he?
I haven't found him yet.
I found the one that he used last semester, and it's not live right now.
Yeah, I don't see him.
Yeah.
It's just his name is just Dr. D on it.
But you can actually see him though.
Yeah, I have his page. It's not streaming right now.
Hey, did you guys go into your capstone meeting for week 1 yet?
Yeah.
Yeah.
Yeah, I did.
What were you supposed to do for the introduction? Because I posted it and then she reassigned it to me.
Really? The PowerPoint?
Yeah.
It should just have a picture of you, what your major is, and an interesting fact in your name. So if you did all
That's what
that, she shouldn't have reassigned it. I would just have to again.
I mean, it wasn't a selfie.
No, mine wasn't either. It's just a picture, but it was of my face.
So when is there a second meeting for that class this week?
Not this week, I don't think. I think it's next week.
You don't have to go to it.
Sign up for the meeting.
You do have to meet with your
team.
Yeah,
Yeah, I did that already.
Oh, you did?
Yeah. How are you guys? How do you
Same
guys
here.
like your teams?
I don't even know them.
Dude, my team is on the ball. We have this one Asian girl named Theen, and she's
she's
on
great.
top of it, man.
Do you
Yeah,
guys
she's
know
great.
who I have? Well, I know Matt Dina is in mine.
Mhm.
And then do you know who Ben Leonard is?
Ben, I know a Ben. I know the nerdy little Ben, but I don't know if it's the same one.
It might
Are
be.
you talking about Ben S. Christian?
Yeah, I think dude, that
He's
dude's
in my
cool.
group.
Yeah, that
He's a
dude's
cool guy.
I have Ben, and then I have someone named Hayden, but I don't know who that is either.
I don't know.
Oh, I know Hayden. He's a good guy.
Oh, really?
Yeah.
Who's your project? Oh, we talked about this
direct
last
controlled
time.
engine valves.
Yeah. So, is that like one of the ones that was proposed by industry, or is that the?
I don't know, but I know mine's the one that has 3 different sections.
What do you mean?
There are 3 groups doing direct engine valves.
Oh.
So,
Do you guys know if anyone made a force sensing gate analyzer? Do you even know what that is?
I've heard of that. Somebody I know is doing that one.
I am too.
I'll get to.
Because none of us in my group, in my capstone group, actually made the project in project management. So we're all
oh
like,
yeah, we didn't either.
what are we doing?
Yeah.
What's the scope of the project kind of thing?
Yeah. Wait, so Chris,
Who's your mentor? Who's your mentor for that one?
Cassandra Wright, I think.
Oh, okay. Dude, I would talk to Bullock because he knows a lot about that stuff.
So he's my mentor.
Dude, you're set. Bullock is like, I think he's the head of the engineering department, actually.
Yeah, he's cool. Like I had my first class with him yesterday, and it seemed all right.
I
What'd
think
you
he's
have with him?
head of MEs, not all engineering. I could be wrong.
Yeah, all my group, all 4 of us are MEs.
Yeah.
They did not.
I have a biomed, I think. Maybe not. I don't remember.
I got 2 MEs and then two BMEs.
How did they pick those? Was it just random?
I don't know how that process went down. I would love
Seemingly
to know how it went down.
That would have been cool if we could pick ours.
We just do our own. I had ideas for what I wanted to do, but
Really?
Yeah, but it's not. It wasn't legal in every state yet. Well, while we're here, y'all want to say what's up to my homie? Hey, come here. Come here. This is Kobe.
What's up, Kobe?
What's up? It's Kobe the dog right here. All right. That's enough.
What's up, guys?
We're first.
Didn't realize that.
All right, I'm going to mute.
Okay, me too.
Hey, Sean. How's it
Hello,
going?
Matt.
Haven't talked to you in a while.
Unmuted because we
What?
do-
Hey,
we
Christian.
shall remain unmuted.
Okay.
Dude, Tron, what time is in Hawaii right now, bro? You're tripping. It's still 7?
It's 8. Oh, it's 9.
What's 9?
Frick that.
Your class starts at 6:45.
What the what?
Oh yeah,
In
bro.
Hawaii, bro.
Oh, okay.
Jeez.
I thought it was more than 3 hours. Is it only a 3-hour difference between?
Yeah, it's only a 3-hour difference from
I
Arizona.
knew it was early.
Who's gonna
because
have their free time?
when I first like opened the class, I went to your camera. You still had the bags in your eyes, like, yep.
Oh, yeah, I woke up looking
He
beautiful.
just
man.
woke up.
What are you talking about?
Arizona doesn't have daylight savings time, so it can change between 3 and 4 hours from Hawaii.
Dude,
No,
how
yeah, we
is
don't
it?
have
Are you on
the
campus
time to
already,
police
Daniel?
states.
Guys.
Yes, I've been on campus all summer. I work here.
How is it right now? Is it packed or no?
everyone just kind of started moving in, so it was completely dead over the whole summer. But now people are starting to move back in. It's a lot of life leaders and sports.
Thank you. I didn't want to have to, but you guys made me. I did the clapping. I did it all. All right.
That was you clapping? I thought that was his background.
No. Burn. Sick burn. Sick Zoom burn. All right. Anyway, let's talk about it, right? This was, you guys did great. I want everybody to know that I think that you all did great. This was a trap, right? This was a trick problem. There was a trick to this one. And it's having to do with the preload. So the one thing that we need to remember here, right, is that we are talking about things starting in an equilibrium position, right? So I'm going to share my screen. What's up? Hold on. Share my screen again. There we go. Got some chats. All right. So what are we going to do, right? Well, we're going to do the things that we did. You guys all got the free body diagram going. You guys had your inputs, your outputs. You had your mathematical truths, right? So let's run through it, right? And we'll talk about it when we get there, right? So here's my free body diagram. It's going to look very similar to what everybody had. And I had my coordinates drawn X and Y, right? So if I was going to do a KD, it would look something like that. You can pick whatever, again, pick whatever coordinate system you want, right? And that is fine and good. Okay, good. Having seen most everybody's work, right? This is where everybody was for this point, and that was fine. All right. So inputs and outputs. What is my input? Well, in this situation, it's tricky, right? We're gonna leave it for now. We're gonna talk about it. It's technically gravity. It's technically gravity, right? So why don't we just say it's mass times gravity? It's technically the weight is the input, right? We're doing that. My output is X, right? It's the change in position. The change in position. All right, mathematical truths, right? It's where we all write down Newton's second law. I say, well, my damper looks like that, and my spring looks like this. However, we are starting this from an equilibrium position. And if this was in an equilibrium position, the most easily calculatable one is a static equilibrium position, right? It's just hanging there. It's just hanging without doing anything, right? It's just not accelerating, right? So in static equilibrium, all right, so let's go down to our reduction here. We're going to reduce these equations. If I reduce this, I'll get mx double dot is equal to negative b x dot minus k x plus mg, right? So that's just all my forces, right? Sum of my forces is equal to mx double dot, right? Remember, I have downward as positive, so upward is negative, right? That's why this looks like this. And I'm not going to do anything with this yet. Why? Because assuming the system is in static equilibrium, that means that at static equilibrium, x double dot is equal to x dot is equal to 0 at static equilibrium. Okay. All right. So let's analyze this when this condition is true. If I analyze my equation when this condition is true, right? Well, I'll get 0 is equal to 0 plus kx, or sorry, minus kx plus mg. So at equilibrium, right? So at equilibrium, we get kx is equal to gravity, right? So Cool. So if this was just hanging out, right? If you just had this sitting in the center of your room with the spring connected to a mass, just sitting there, the spring force would have to equal the weight, right? That's what it would have to be. So at static equilibrium, that is the case, right? So at static equilibrium, that's the case. Okay. Okay. Cool. So how do I determine what that deflection is, right? So instead of using x here, I'm going to use this variable delta. I'm going to use the lowercase delta, right? Because I want to figure out what is this delta? What is this delta? Because we're not starting from the free length of the spring. This is starting in a deflected position. So delta, by doing some algebra, is just my weight divided by k. Okay. So this is the distance that's going to cause the preload spring force, right? Because really what this spring force is, really what this spring force is, right? Really what it is. Let me get another new slide here. One more. Yes. So really, how I can define F sub k here is k delta plus x. And you're all like, well, that's cheating. You never, now you know. Now you know. Because what happens if I introduce this into my equation, right? Well, I'll get mx double dot plus bx dot plus k times delta plus x is equal to mass times gravity. Okay, but wait a second. Didn't you tell us? Didn't we just find out that delta is mg divided by k? Hold up. Yeah. That goes away. Oh boy. I've got mass times gravity on both sides here. That goes away. And that is our equation. Why is that important? This is a huge thing. This is a huge thing. Why? Because regardless of orientation, if you start from an equilibrium position, the mass of the object, the weight of whatever it is, doesn't matter if you have a spring. It's already taken into account in the preload. That's it. So it was a trick. You guys all did really well. You did. Basically, everybody tied except for one group. So everybody tied for second, one group got it. All right. So it's going to be a tight tri-quizzer this week. All right. You guys have any questions on this problem?
Yeah. So real quick, are you saying that the preload was already calculated, so we just did all that work for nothing, or am I getting that wrong?
Cody, when you say you did all that work for nothing, I don't know what you mean. So the preload exists, right? Unfortunately, I don't have a spring with me. Well, I have one, but it's not an extension. Try to do it with this, okay? So imagine for a second this is my spring, right? If I was to hang this from the ceiling, right, this is going to extend by some length, right? And it's just hanging out there, and I haven't disturbed it. So there's already a force in that spring that is equal to the amount that I'm pulling it down, right? If I then move that some more, this is going to extend more, and if I let go, it's going to come back, right? So I don't know that all the work that you did was for nothing, but you proved to yourself that you don't need to worry about the weight of the object itself, right? We proved that this result is agnostic of orientation. So if I have a spring system that's vertical or horizontal, it doesn't matter. If I don't have a force pulling on it actively, then it's going to be equal to 0.
Okay.
All right. All right. Don't think we have time for anything else.
What is set in that preload, Dr. D?
What is setting the preload?
Yes.
Let's go back to the picture. It'll be easier if I draw a picture. Next class, I'll have a mass and a spring, and I can show you. But here, so what's setting the preload is the actual weight of this block, right? This mass. So when you're hanging, if this was hanging, just hanging from like the rafters, right? And you just had a mass hanging on a spring, that spring would extend based off of the weight, right? So I'm saying because we're starting at this point where we're already in static equilibrium before I analyze the dynamics of this system, there's already a preload taken into account. So as long as you are using equilibrium points to set the starting point of your system, you don't have to worry about the mass of the object or the weight of the object.
Just another thing, just making sure, because it could be tricky. Preload can also be determined in terms of compressing the spring. It doesn't have to be pulling on the spring, right? It could be, okay.
Yeah. I mean, if you flip this around and it was sitting on top, right, there would still be some deflection in that spring. It would still be wanting to push back on you, right? So you still are storing some energy in that spring.
Okay, so any deflection before anything being put on the spring is considered preload.
Yes. All right. We are going to cover, we'll start this stuff on Tuesday, obviously, because we're over time, but I'm going to get to the end. Oh, no. Don't have time. All right, deep thoughts from Dr. D. Unfortunately, I don't think we have time for that either, so I'm just going to throw up the thing. All right, this is the first one. How's everyone feeling about class? I'll move this so you can see the thing. The end of week 1. Pretty neutral. All you have to do is hit the picture. Just touch the screen. I know that was fast. I apologize. We got a lot of stuff to cover. Start working on the lab. If you don't have a partner by the end of the day tomorrow, let me know and I'll help you find one.
How do we answer the poll again?
You open it up and you just click on a picture.
How do we open it up?
Yeah.
There's no link or anything in the.
Trenton, everybody gets points regardless of whether I was able to meet with you or not. You guys were likely at the same point as everyone else. So since nobody else finished it, everybody else gets second place points. That's how
I put the link in chat.
So,
May I ask, how would when we do time trials again or whatever, yeah, like how will this work if like some people are going to be in class and some of us are going to be online? Like, are they going to have to get their laptops out and like join the Zoom call?
Yes. 100%.
Okay.
All right. And then I'll leave you with this one and you guys can, if I can switch slides maybe. Next one. Next slide. I would like the next slide, please. Okay, hold on. Cool. Well, there we go. All right. Awesome. We are done for today. I apologize for going over again. I really don't want this to be a thing. I will try my best to not do it again. You guys have a great weekend. Please, please, please start the lab before Tuesday night. Please, please, please start the homework before next week on Sunday. Come ask questions. Have a great weekend. And I will I'll see you on Tuesday. All right.
Hey, Professor.
Thanks, Dr. D. Bye.
Professor, I got a quick question.
Yeah, what's up?
So I accidentally thought that the capstone meeting was right now, but it's actually in about 40 minutes. The trick part of the question was that the whole system was in equilibrium. That was
Yeah.
the trick.
Yes. We're always going to start from equilibrium. Always. It just makes life a lot easier, right? You guys will find out that I'm fairly lazy, and I don't like to do a lot of extra things that I don't have to do.
Okay.
Fresh,
Also, by the
fresh.
way,
What was that?
I was just saying that's fresh.
by the way, BMEs get solid mechanics, but it's all about statics, and
Yeah.
we don't have any dynamics.
No,
related.
Dr. Jones says that he spends a lot of time doing stuff with internal forces and with you guys. So
Yeah.
Professor, I have a quick question.
yes.
Are we supposed to, let's say, and possibly have the same lab days? Well, like, for the in-person class with our lab partners. Let's say if I'm supposed to be there on Tuesday, and she has to be there on the Thursday, is that a problem? I don't know how that's
No,
supposed
as
to
long as
work.
you're both 9:45, I don't care.
Okay, all right,
So
perfect.
if you want to group with somebody who's on Tuesday and you're Thursday, it's fine.
Okay.
Cool.
Hey, thanks, Dr. D. Real quick, do we only meet Wednesdays for robotics, or are we meeting tomorrow too?
Only on Wednesdays.
Sounds good. See ya.
Yep. See you, Cody.
Just for the participation, is there anywhere you want us to send the Funko Pop avatar?
Mostly smoke signal would be best. It doesn't matter. Email. Some people drop them in private messages in Discord. If you want to use private message in LabCloud, that's fine. Doesn't matter. As long as I get it, it'll be fine.
Awesome. And I had another question about the lab. So I noticed that on your YouTube playlist, you posted a video on that. Do you want us to use those results, or do you want us to create a pendulum in SolidWorks and then follow the instructions that were posted in topic 1?
No, I want you to use the video, please.
Use the video for the lab?
Yep. Yeah,
Awesome.
use that as if you were in class doing the actual lab. It's just that you took it home. You took a video home of it, right?
Awesome.
Yeah.
Eddie, I'll send you a message in a bit.
That works.
Sounds good. I've been looking for a partner all morning.
Sweet. Me too. All right. Later, man. Thanks, Dr. D.
No problem.
See you, Dr. D. Really enjoy this class. Thank you.
Thanks, Alex. See you guys. James, you just hanging out, or 'cause I'm gonna leave. All right.